All right, so as promised in my last video, I was going to talk about chemical equilibrium. So we're going to begin slide 1 on chapter 13 about chemical equilibrium. Again, always on slide 1, we have our book problems for this particular chapter. All right, now sometimes reactions do not go to completion, but rather go to an equilibrium between the products or reactants. Okay, now up to this point, we've really only talked about reactions as though they went completely from our reactants all the way to the products. Okay, but now we're going to talk about the equilibrium that forms sometimes where we have a forward reaction and the products then produce our reactants. Okay, now this idea is of reversible chemical reactions. So let's say that we mix H2O gas and carbon monoxide gas. First, the reaction is going to go forward, consuming those reactants that we put in, and it's going to make products. Okay? The products that we end up with are H2 gas and CO2 gas. Okay? Now, eventually, we're going to make enough of those products, the H2O and the CO2, that they're going to want to go backwards, and the reaction is going to go in reverse. So we're going to end up building enough of these, and then they'll end up going back to form some H2O and CO, and so we'll have a competing forward and reverse process. Okay? Now, notice that there is now an equilibrium between our forward and reverse reactions, which we denote with this special arrow, where we have one arrow going forward and one arrow going backward. Okay, that's going to denote equilibrium. All right, now moving on to slide 3, we're going to start talking about different types of equilibrium, the first of which is dynamic equilibrium. Okay, so in our last video, we talked a little bit about dynamical equilibrium or dynamic equilibrium, all right, which was basically when our forward reaction rate was equal to our reverse reaction rate. Okay, now notice for a particular reaction, if it is a dynamic equilibrium where the forward equals the reverse, then those arrows are going to be the same size. We'll get to a case in the future where they're not the same size. Okay, but if we have them being the same size, it will be dynamic equilibrium, okay, which means that our forward and reverse reaction rates were equal, right? And that was what allowed us to equate those two reactions going forward and backward so that we could get rid of that intermediate in our reaction coordinate and in our kinetics, okay? Now, equilibrium doesn't mean that our concentrations are equal, but rather that our rates are. Okay, so if you look at slide 3, what you'll see is that plot where we have time on our x-axis and concentration on our vertical axis. Okay, and we look at this reaction here where we start with our product, or sorry, where we start with our reactants, right? We have H2O and CO gas, right? And we could either use the H2O or the CO for our kinetics. Okay, so looking at our rates for the H2O or the CO, notice that our reactants are going to drop in concentration as they get used up, okay? And as we use up our H2O and CO, we're going to be building up our CO2 and our H2, okay? So, but once we end up building up enough, right, then our reverse reaction is going to happen, okay? So notice that our rate of change was very dramatic at the beginning, but it sort of stabilized at some point, okay? When those rates sort of stabilize, we enter into an equilibrium region, okay, where our rate for this process is basically the same as our rate of change for that process, the forward rate being about equal to the reverse. So everything before this dotted line would be everything we talked about in chapter 12 about kinetics. Okay, and now we're going to be starting to talk about everything after that dotted line, which is our equilibrium process. Okay, so moving on to slide 4. Okay, now here we're going to talk about our equilibrium constant. Right, and we denote this with a big K. Remember that in our kinetics, right? In kinetics, we had a little k for our rate constant, okay? For equilibrium, we have a big K for our equilibrium constant. And a lot of times, since I'm talking about an equilibrium constant, I usually call that K EQ for our equilibrium constant. That way there's no confusion, okay? Now, since our concentrations of reactants and products are not equal at equilibrium, okay? So since our reactant and product concentrations are not equal at equilibrium, okay, then we need a way to relate what we start with to what we end with in a reaction. Okay? Now, since our forward and reverse, reaction rates are equal, at equilibrium, we can define our rate constant, or sorry, not our rate constant, we can define our equilibrium constant using our concentrations at equilibrium. Okay, so not our initial concentrations, but our equilibrium concentrations. Okay, because remember, if we were to look at our plot, right, we saw that our concentrations changed a whole bunch until we reached equilibrium, and then once we were at equilibrium, they sort of stabilized out. Okay, so once we're at equilibrium, that's going to be the best place to determine our equilibrium constant. All right, now, if we move to slide 5, okay, that's going to be our equilibrium constant continued. All right. So how are we going to get our equilibrium constant? Well, let's say we have a reaction, and it's going to be generic, where we have little a, big A, plus little b, big B, in equilibrium with little c, big C, plus little d, big D. Okay, where my little a, all the little letters, are going to be my stoichiometric coefficients, right? And then all of my big letters are my species that I'm looking at, my chemicals, right? Like H2O or CO or whatever, okay? Now, let's say that we have this reaction, okay? Then that means that at equilibrium, okay, we know that our forward rate is going to be equal to our reverse rate, right? So if that's true, then that means that if we're looking at our rate going forward, using our elementary reactions that we talked about, we have a rate constant going forward, right? We had a Kf, and we had a Kr, right? And Kr was the same thing as K minus F, right? But I'm just going to call that Kf for going forward and Kr for going backward. So we have Kf times my concentration of big A raised to the little a, because I'm using my stoichiometric coefficient. All right, and then I'm going to have my concentration of B raised to my little b, so that's going forward. Now going backwards, these are going to be my reactants going in the reverse process. So that means that this has to be equal to Kr times my concentration in C raised to the little c times my concentration in D raised to the little d. Okay? Again, our forward reaction rate was equal to our reverse reaction rate, and these are just our rates from kinetics that we just finished. Okay? So, if we're looking carefully, then what we're going to say is that we want our equilibrium constant to be the ratio of product concentrations over reactant concentrations. All right, so that would mean that our KEQ, my equilibrium constant, okay, that's going to be equal to my rate going forward, KF, over my rate going backwards, KR, okay, which is equal to, and this is the important one, concentration of my products, which is C to the C, over, or C to the C times D to the little d, all over my concentration in A to the little a times my concentration in B to the little b. Okay, where those brackets are denoting the concentration of the particular species. Okay, this is very, very important. We will be using it over and over and over again in this class. Okay, now notice that for this, all of these concentrations are at equilibrium. Okay, so if you want, you can always write a little EQ at the bottom to remind yourself that all of these concentrations are going to be at equilibrium. Okay? All concentrations at equilibrium. Okay, for your equilibrium constant. I know that sort of makes sense, but we're going to have a couple of other constants, and you want to make sure that you're keeping them all correct in your notes. Okay? Also, another thing to keep in mind is that KEQ has no units regardless of the exponents. So it's going to have no units. So even though C has units of molarity, D has units of molarity, A and B have units of molarity, you can imagine a case, right, where we have like A plus B is in equilibrium with C, right? And we don't have any D, right, where we have two reactants forming one product, okay? In this case, right, you can imagine that we would have, you know, KEQ is equal to C to the C, A to the A, big B to the little b, right? Well, if I have, you know, 1A plus 2B gives me 1C, right? Well, then that means that my little c is 1, my little a is 1, and my little b is 2 in this case, right? Well, that would mean that I have units of molarity to the first over molarity to the first over molarity squared, right? Which you think would give us 1 over molarity squared, right? Right, because these would cancel. Yeah, well, that's not what happens, okay? And it's a little bit more complicated, but what you need to know is that when you have an equilibrium constant, just leave off whatever units you have at the end, okay? Don't worry about it, okay? This is the one time in chemistry where we say you don't need the units, okay? So don't include units on your equilibrium constant, okay? Regardless of what those stoichiometric coefficients are, okay? Now, let's see. How much time are we at? Okay, we got plenty of time. So, the next thing that I would like to talk about is on slide 6, okay? And this is the significance of our equilibrium constant, okay? Now, our equilibrium constant is going to be very useful and can tell us a lot about our reactions, okay? If K EQ is much, much greater than 1, okay? So if K EQ is much, much greater than 1, then that means that the numerator of the equilibrium constant, right? So the numerator of KEQ, right, that's going to be our products, is larger than the denominator, right, which is our reactants. Okay, so if KEQ is bigger than 1, then our products, we have more products at equilibrium than we do reactants, which means that products are favored. Right? Very important. Products are favored. It also means, okay, that our forward reaction is favored. Forward is favored. Products are favored. Okay? And that means that if our KEQ is much, much bigger than 1, then we know that we've got more products, okay, at equilibrium. All right? So in that case, right, if the products are favored, then that means that our equilibrium arrow going forward is going to be bigger than our equilibrium arrow going for the reverse reaction, okay? So that would be the arrow that we use if KEQ is going forward, okay? Now, let's see, if KEQ is much, much less than 1, okay, then the reverse is true. So then we know that the numerator is much, much smaller than the denominator. Is that right? Which means that the reactants are going to be much, much smaller than the products. Okay? So that means that we have a case where our reactants are favored. Okay? That's the first thing. The second thing is that the reverse reaction is favored. Okay? Which means that our back arrow is going to be bigger than our forward arrow. Okay? Lastly, if EQ is approximately equal to 1, neither is favored. Okay? So you'll want to know each of these conditions and be able to apply them to a particular reaction. Okay? Now, I'd like to do a quick example, but I think we're going to save that. No, we can probably, yeah, no, we'll save it for the next video. That way we can run through that at the beginning, all right? Because I know you guys want to have a couple of examples. And keep me aware, like let me know if you guys have any issues with the examples. Keep me informed as to if you're struggling. You know, I want to make sure that we give you guys enough of the resources that are going to be beneficial to help you guys be successful, okay? So again, shoot me an email if you have any issues.